So last time we had started this chapter on kinematics of deformation. I told you that what we'll be looking at is to describe, just mathematically describe the deformation or a motion of some solid body or some structure. We are not concerned right now why it is deforming, for example, how the loads are causing it to deform. But all we are trying to see is how can we describe the deformation and how can we measure strains, for example. So that's all we're looking at. I went through a bunch of examples of one-dimensional average measures of strain that you might be used to. Delta L over L is a very average measure of strain that works only in one dimension. And what we're going to look at is how to try to extend that to multiple dimensions and in all directions also. So what I showed you last time was like a what would a full picture of deformation process in 1D look like. So what we're going to denote undeformed structures as is this black bodies. For now, I'm calling it a single scalar Z, and the deformed locations of that body would be shown in blue, and I'm going to denote that with X. And this is a notation that we'll continue to use forward as well. So I showed that if you were to plot Z versus X, then you can map essentially each point in the undeformed location to its corresponding location in the deformed configuration. And that allowed us to define something called local stretch. So stretch is not going to be an average measure over the entire length similar to strain. It is going to be a local at a measure at a point. So when we talk about stretches and strains, these things are always at a point. These are fields. They vary from point to point, right? So at a location Z in the undeformed coordinates, in the undeformed configuration, we are going to say that if we take that and multiply that with the stretch, we are going to get the new length of that infinitesimal body. So small infinitesimal dz goes to a dx. And that allowed us to define this stretch quantity z, which we will try to extend to multiple dimensions, as we go on. So let's see how we can generalize this concept of going from an undeformed location to a deformed location in multiple 2 or 3 dimensions. Last time we were also looking at things that this deformation map can be expressed as vectors, as a vector function given some body in the undeformed black configuration. You apply some vector function to it to get its corresponding one-to-one location in the deformed configurations. We looked at translation, we looked at uniform expansion. So in both these cases, we had the z plus some constant displacement u for each and every point. That was translation. For expansion, we said that if you have the undeformed coordinates z, just scale it by some alpha, and that would give you the deformed coordinates of that point. And about this is where we were last time, where we said that let's try to examine a map that could potentially be the bending of a simply supported beam. So I also mentioned that this is not really how the correct map for a simply supported beam of how it would bend. But this is just as an example of what would happen if you apply some distributed load on top, fixed pinned at the left end, roller at the right end. This right end might slide left by amount delta 1. The middle point might go down by an amount delta 2. And using these two quantities, delta 1 and delta 2, we came up with this map saying that x1, x2, x3 will be given in terms of z1, z2, z3 as these functions. What are these functions? In the z1, in the axial direction, z1 direction, we are saying that any point that was originally in z1 will get shrunk or will get moved to the left by an amount Z1 minus Z1 over L times delta 1. So all we are doing is scaling the right end back by an amount uh, by the factor of its length Z1 over L. Z2, we are saying that that would look like some sort of a sinusoidal function. So if initially a point was at height Z2 in the above this bottom line here, then the final deformed configuration would be Z2 minus delta 2 times sine of again the length. And you can verify that when Z1 is equal to L, what is the value of this sine term here? When Z1 is equal to L? 0. Sine of pi would be 0. That's this point. We don't want that point to be moving vertically. When Z1 is L over 2, which actually is something we'll do in a bit, when Z1 is L over 2, what is the value of that sine? 1, right? When Z1 is L over 2, this becomes pi over 2. So sine of pi over 2 is just 1. And what we are saying is that a point that is at half the span will go down by an amount delta 2. And we are assuming that there is no change in the depth Z3 direction. So that's example of a approximate map of bending. And these are just examples to try to help you to visualize how you can describe a deformation process. Given the initial coordinates, I just want to know where it went. That's all that this map or any map up here, that's all that this map does. Describes, connects the initial and the deformed configurations. So let's take a minute here and you tell me where does a point that initially lies on Z1 equal to L over 2, Z2 could be anything, so it's basically representing this middle cross section, this black cross section, and Z2 and Z3 could be anything. So that for black cross section, where does that go in the deformed configuration? So take a minute, see if you can set up in terms of Z2, Z3, where will any point on that cross section go in the deformed configuration? You're already given the map. Go ahead. What's the first component? X1. Okay. Z1 minus, if I put this L over 2, then I get delta 1 over 2. So I'll put that here. Z1 minus delta 1 over 2. That's just saying that whatever, that this black cross section would move to the left by an amount delta 1 over 2. Okay. What about X2 and X3? Okay. So Z2 minus delta 2 and Z3 would remain unchanged. Right. So what that is saying is that yes, it moves to the left and it drops down by an amount of delta 2. The entire cross section, all points just move to the left by delta 1 over 2 and drop down by delta 2. Question, Kelsey?
I guess for X1, why did you change the Z1 to L as well?
Say that again.
So like you have Z minus 1 or Z1 minus delta 1 over 2.
Yes.
Why is it not L over 2 minus delta 1?
Why is it not L over 2 minus? I see. Yes, you are right actually. So Z1, since I'm looking only at these points, it's not Z1. It is indeed L over 2. Is that what your question was, April 2?
Yeah.
Okay. All right, so this is a way that you can sort of visualize how this map works between deformed and undeformed configurations. And as I said, this was not an exact map, but this one is. This is an exact solution to a problem that is a cantilever beam with a rectangular cross section with a moment m applied at the end. And so if you have a beam in pure bending, let me ask you this. If I have a cantilever beam fixed at the end, if I apply a moment here, what does the bending moment diagram look like? Constant value, right? Rectangle, because bending moment m here is, if you take any cross section, it will be the same bending moment m throughout. So constant bending, which is an example of a pure bending. If the moment is uniform across a beam, it's called pure bending. In pure bending, we'll see later on that beam theory says that a beam would turn into an arc of a circle. Okay, if you apply enough moment, it would kind of bend over and become a complete circle by itself. Here, this in this book, very sort of well-known book on conventional uh, theory of elasticity, Timoshenko and Goodyear, they give you an exact solution to this beam under small deformations. So they do assume small deformations for this. And here's what this map says. Initially, the beam is laid along the z-axis. Their z-axis is our z3 axis, and vertically down is the x1, and y would be pointing in or out. Y would be pointing in, so that x cross y gives me z, right? So y is pointing in, and the cross section looks like that. When you apply this moment, indeed the longitudinal bending of that beam does look like a arc of a circle, but even the cross section deforms. This is something counter to what you might have learned in beam theory, that the cross section remains plane and undeformed, right? Cross section remains rigid, but in reality, cross section does not remain rigid, it does deform. The outer two edges curve in, the top surface curves up, the bottom surface curves up. So if you look at this curving up this way, the curvature here is in the opposite direction. But anyway, so take a look at this map as well, and this is an example of a map that connects, again, the undeformed location that is given by Z, and they give you a displacement field, which means that you can add this displacement to each and every point Z1, Z2, Z3 to get its corresponding position in the deformed coordinates. So these are just examples of common deformation maps. Okay, we're going to use these deformation maps and to try to come up with measures of stretches, strains, try to figure out how deformation changes from point to point, and that will allow us to extend the ideas of strain from 1D to 3D. Okay. All right. Quick note before we proceed. Now, I think this is probably not mentioned in your textbooks, but typically people look at deformation process in one of two ways. Something called a Lagrangian description of deformation and something called Eulerian description of deformation. The difference is essentially what you realize is that it's the same deformation process, but there are two ways to look at it. One way to look at it is that if I have this body, I will go to a particular point Z in the undeformed location, and I'm going to track the deformation of that particular point Z as it deforms to the final configuration. That point of view is called the Lagrangian point of view. That I'm going to go to this Z and track each and every point from its original undeformed location. Therefore, displacement would be a function of the undeformed coordinates Z. Everything will be expressed in terms of Z. That's Lagrangian point of view. Now that works very well for solid bodies and structures. We know where initially the point was when we constructed it. When we apply loads, it deforms, so we can track the deformation of that point. It does not work so well for fluid mechanicians, where you have a space through which some fluid is flowing. And all you can say is that at this point, at the current time, let's say some point x, what is the velocity of that point, uh, of a point that is currently at a location x? So what the opposite Eulerian point of view says, I'll go to some point in space and I'll visualize material deforming and kind of flowing through that space. I'll stick to that point in space. And at some instant of time, I'm going to tell that, okay, the point that is there at this instant came from some location. The displacement of that point in space is given in terms of x. So everything is expressed in terms of x, that is the deformed coordinates of a point. Now, the good thing is that if you know the map, you can easily connect the undeformed configuration to the deformed configuration. They both are obviously equivalent. They are describing the same process. So let me take an example here. We looked at the uniform expansion example, right? What was the map for the uniform expansion? Okay, alpha z, right? So x is equal to alpha z. What is the displacement in the Lagrangian description, that is as a function of z? What is the displacement of a point that was originally at z? It would so the displacement is always defined as the current position minus the original position, correct? Which is nothing but alpha minus 1 times z. So you tell me what point you're talking about, I can immediately tell you what its displacement was in this form, alpha minus 1 times z. That's the Lagrangian way of describing things. Okay. How about the Eulerian way? UE as a function of z, both u and z are vectors here. That also is x minus z, but now instead of expressing x in terms of z, I'm going to express z in terms of x, which is equal to x minus phi inverse of x. Phi inverse is basically the map, inverse of the map. So if you see, that's very easy to calculate. Z is equal to 1 over alpha x. And what we get here is x minus 1 over alpha x, which is 1 minus 1 over alpha times x. What this description, the second Eulerian description, says is you go to any point in space, okay? Go to any point in space. I have some particle that arrived at that point after deformation, okay? And the displacement of that particle is going to be given by this expression. And you can verify they both are going to give you exactly the same result if you fix the initial point z. Okay? Just two alternate ways of describing things. Fluid mechanicians prefer the Eulerian way because they don't really know what the map is, or they can't really track each and every fluid particle as it deforms. For solid mechanics and for structural mechanics, we prefer usually the Lagrangian way of describing. Vikita? Excuse me.
Can you explain that Eulerian expression?
Say it again.
The Eulerian expression.
Oh, explain it again. So you agree displacement is final position minus initial position. I can express z as a function of x just by inverting this relationship. And since z as a function of x is just inversion of that map, all I've done is replaced this z with 1 over alpha x here. And that gives me that, okay? Any other question? Go ahead, Bill.
Shouldn't the Eulerian be a function of action instead of z?
You're right. So this indeed should be a function of x, not z. Any other question? All right. So this was just sort of an aside so that when you, maybe if you're reading some other book on mechanics, you don't get confused by these two terms, Lagrangian and Eulerian. We will essentially be following the Lagrangian point of view. Okay, now back to trying to extend the idea of stretch and strain from 1D to 2D and 3D. What we're going to try to do is to do some imagination here. I have a 3D body that looks like this with a hole that I've shown again and again in the notes. After application of loads, that black configuration deforms to this blue configuration. That's something that we are comfortable with now. What we're going to try to visualize is how do individual lengths that are sort of embedded in the body, how do they change? We sort of understand what stretch means in 1D, right? If I give you a length, if I stretch it, the stretch is final length divided by original length, right? Or another way to visualize this is that the stretch lambda takes the original length, multiplies it with lambda, and gives me the final length. Okay, we are going to try to apply the same principle on curves now, not just straight line segments. So for example, I have one curve here, which indeed is actually a straight line segment, C1, which is, I'm saying, Z, set of all points Z that are given by Z1 is 0, Z2 is 0, and Z3 is given by S, where S, the parameter, goes from 0 to 1. So you can imagine these are all sets of points for which Z1 and Z2 are 0, and Z3 is given by S, where S goes from 0 to 1. So that's my curve C1. Similarly, curve C2, it's a little more complicated. It says Z1 and Z2 are given by R sine of something, R cosine of something, and the third coordinate is given by Z. Can you tell me what this C2 kind of looks like? Have you seen this curve before in a homework maybe? It's very similar to the curve that goes around the cylinder, right? So it starts off from this point on the x1 or the z1 axis, and it goes, the black curve kind of goes around and around in this way. When s is equal to L, I get sine of 2 pi. So over the length of its parameter, it goes around one circle. That's what this curve is doing. So it goes around one curve. Kind of a weird curve, but you can imagine there are infinitely many curves in this body. You can pick up any set of points that describe a curve, and that's a valid curve to look at within the deformation of this body. What I've also drawn here is the deformed locations, the approximately deformed locations of these curves in the blue configuration. So now the question becomes, if we want to extend this idea of stretch and strain from 1D to 2D and 3D, let's try to figure out first, how do these curves change from undeformed to the deformed? The C1 curves initially was a straight line. Phi of C1 is this deformed curve like here. C2 also correspondingly gets deformed. And how do we describe these curves now? Any idea on how can we describe the curve in the deformed configuration if I'm giving you the undeformed configuration?
What is the deformation?
Say it again. Let's assume that the deformation map is given by phi of z. Okay, that's some function of z. I'm giving you what z is. Can you tell me what x, the final deformed locations of those curves, would be? That's right. So it is indeed given here. All you will do is to apply the map consistently throughout to each and every point of that curve. So C1, the set of points C that were originally at C1, will go to phi of C1, which is a set of points x that are given simply by applying the map phi of z. So whatever that map is, you will simply take that map will connect each and every point z, which is a set of points 0, 0, and s to its corresponding new locations x here. So let me write that fact here, that we know what z looks like uh, given a parameter s. We will apply that same s parameter. So the idea is this. For example, let's take a look at the tip of this point. The tip of that point is 0, 0, 1. Do you agree? All right, so that point at 0, 0, 1 will go to um, the, the, the location that is given by phi of z, which will be a set of points x1, z1, z2, uh, z3, which are themselves a function of s. Similarly, x2, z1, z2, z3, that are themselves a function of s. And similarly, x3, z1, z2, z3, that are function of s. Another way to visualize this is in terms of one of the examples that we looked at. So for example, pick this point in let's say this, let's pick the center point on the black plane. That center point is um, z1 is equal to L over 2 and z2, z3 are 0. That point would uh, go to L over 2 delta minus 2 and z2 minus delta minus 2, and z3 would still be 0. So that point goes from here to here. And that, if you imagine a curve, that was originally out here, the end point is what we were talking about there, that curve would get deformed to something like this. And essentially this map allows us to go from each and every point to its corresponding um, deformed location. Now, what we still haven't talked about is how does it, do you imagine that those, would the length of that curve change as it goes through this deformation? In general, if I have this body, there is infinitely many possible curves embedded in this. If I bend it, do you think that the length of those curves would change? In general, yes, right? For example, in a beam, if I have a beam, if I bend it like this, the top fibers here are in tension, bottom fibers here are in compression. All these fibers are examples of curves. So tension fibers would increase in length, the compression fibers would decrease in length, and indeed that is exactly what we want to figure out. How does that happen? How can we describe that process if we know the map? Okay, all right, let's do that. First thing we'll need to describe how a curve changes its length is something called the tangent vector. I had this original undeformed curve. That curve, a tangent vector at any point of that curve is given by dz ds, which is basically nothing but 2 points at s and s plus delta s. Okay, so I'll imagine 2 points along that curve at s and s plus delta s. You give me a parameter s that corresponds to some point on that curve. S plus delta s would correspond to a point slightly later on that curve, right? So the tangent to the curve will be given as z at s plus delta s minus z at s divided by delta s with the limit delta s tending to 0. Do you agree? All we are saying is that this second point that I have up here, as I bring it closer to the first point, I'll get a vector which will be pointing in the tangent direction to that curve at that point. As I go to a different point, the tangent vector will be changing. So you can clearly see the tangent vector is pointing this way. Maybe I'll draw some tangent vectors here. Tangent vector is pointing this way, this way, this way, this way, that way. So tangent vector keeps on changing as we go along the curve. Okay, and that's of course a complication that comes up because our curves are expressed in 3D. It's not a straight line. For a straight line, the tangent vector is always along that line. This was a tangent vector to the undeformed curve. Let's see what a tangent vector to the deformed curve would be given as. We are saying that the tangent vector would be the same parameter s, derivative with respect to the same parameter s of the deformed positions x, dx over ds, which is nothing but x as a function of z as a function of s plus delta s minus x as a function of z as a function of s divided by delta s with the limit delta s tending to 0, and again that's the set of deformed tangent vectors to the curve in the deformed configuration. Why do we need these tangent curves? Anybody remember how we calculated the length of a curve in 3D? How did you guys calculate the length of a curve of that spiraling curve along the cylinder? Say it again. Integral of dz or integral of dx vector, right? Maybe I'll pull that up right here. So if I have a curve, initially we looked at dx dz was the tangent curve, and the length was given as integral dl. Integral dl was nothing but integral of dx, which was dx ds times ds, which happened to be the integral of dx1 square plus dx2 square plus dx3 square. That was the Pythagorean theorem way of understanding that, right? So to find the total length of a curve in the deformed and the undeformed configurations would be very similar to this. I don't have a lot of space here, but let me see if I can write that maybe up here. The total length L0 of a curve in the undeformed configuration would be integral dl0, which is given as integral dz ds magnitude and ds. Let me ask you this: if you're given the parameterization of a curve, can you do this integral? What does this integral look like? Integral dz ds if you're given the parameterization of a curve. All you need to do is to take the z1 with respect to x, derivative of z1 with respect to x, z2 with respect to s, z3 with respect to s, square root of sum of squares, exactly like I showed you here, and integrate that, right? That is an integral that you have done for the spiraling curve. Now the question is, can you find a corresponding integral? Can you find a corresponding integral for the deformed curve? How would you define the length of a deformed curve? So instead of z, all we need to do is to have x, right? There are two curves, the black curve and the blue curve. We have parameterizations for both of them. Why? Because we have the parameterization for the undeformed curve, and the map gives me a parameterization for the deformed curve directly. Okay, so if you have the parameterization to some curve, and if you have the map, no matter how complicated that curve is, you can find its length in the deformed and the undeformed configurations. Okay, and of course that integral would be given by L equal to integral dl, and that would be integral dx ds magnitude ds, which you will see we can replace as lambda s dz, to move that a little bit here, dz ds magnitude and ds. All I've done here is replaced dx over ds with lambda times dz over ds, which is basically what the definition of the stretch was in the first place. Stretch is something that takes tangent vectors from the undeformed configuration to corresponding tangent vectors in the deformed configuration. Okay. Um, so you can visualize this stretch, one-dimensional stretch, as something that takes this undeformed tangent vector to this deformed tangent vector, and correspondingly does that for each and every point as the value of s changes. S is equal to 0, we are talking about this tangent. Keep on increasing s, we are talking about the corresponding tangent up there. Okay, so this seems kind of a convoluted way of expressing it, but what this allows you to do is to basically say that as long as I know the parameterization, as long as I know the map, I can do both these integrals without any trouble. And the integrals themselves might be complicated, that you might have to use some numerical integration, but you can at least set up the integral and pass it on to something like MATLAB to compute those integrals. All right, so that's still just connecting. All we did here was to try to extend the idea, this idea, that is along a straight line segment. Along a straight line segment, if you give me undeformed configuration, I can tell you where what its length would be in the deformed configuration. We are extending this idea from a straight line segment to something that looks like some curve. Could be as complicated as you want, as long as we have the parameterization. All right. That still does not allow me to tell what the picture of strain would be in 2 dimensions and 3 dimensions, because it sounds like I would have to consider all possible curves in all possible directions, right? So if I am at a point, I'm trying to figure out what is the strain at that point. The strain, as we know, would be a tensor. We would have to look at curves at that point that are pointing in all possible directions, so that the tangent vector to that curves would give me vectors that are pointing in all possible directions. So to try to extend this idea to a more general setting, what we'll do is use some basic math here. We'll note that the tangent vector to the deformed configuration is just dx1, dx2, ds, dx3, ds. And if I use the chain rule, just basically to try to expand this idea, that dx1 can be expressed in terms of z as dx1 dz1, dz1 ds, plus dx1 dz2, dz2 ds. All I did the first term here was apply the chain rule for x1. For the second term, apply the chain rule to x2, apply the chain rule to x3. That's all that I did here. I hope you agree that these tangent vectors are exactly equal to this expansion, just given in terms of z rather than x. Okay. And then in the next step, I'm writing this entire thing as a matrix times a vector. You can verify that if I take these three, multiply them here, I get the first term up here. And this basically allows us to generalize this idea of stretch from a one-dimensional concept to something that works in all possible directions. This is what we call a deformation gradient. Why do we call it a deformation gradient? Because you look at the terms in here. The terms in here are partial xi, partial xj. Hope you can verify that. Partial xi, partial xi, partial zj. Okay, and I'll come to that also. This is indeed a tensor. It's a gradient of a vector field. So that's why it's called a deformation gradient. And when multiplied with the undeformed tangent vectors, it gives me the deformed tangent vectors. So one way to write that would be to say dx ds, maybe I should write that in blue, as deformed, is equal to F acting on dz ds. Okay, this F is represented, or F is written in many different ways. So uh, this is a very important relationship. So another way to think about F is that it is the gradient of x with respect to z. So note that how I'm writing it. And since the result is a tensor, I'll put a tilde underneath that. Gradient of x with respect to z, and that results in a tensor. Another way to write that is that F is, sorry, this is not tilde, this is equal to, and this is not a tilde, this is also an equal to x dyad with grad. And that gradient is with respect to z, not with respect to x. So these are all equivalent ways of writing this tensor F, which is going to be the most important tensor to try to understand what it means. All that this is saying is that I have two vector fields. One vector field is the set of vectors in the black undeformed configurations. The other vector field is the set of points uh, in the blue deformed configurations. They are both respectively given by z and x. And if I take the gradient of x with respect to z, then that will give me something that will capture the deformation in all possible directions at any given point in the body. Okay. All right. So let me see if we can try to describe this in components. We've already done that. What we did on the previous page, let me ask you this then. Is there a shorthand way of writing this using indicial notation? Okay, yeah, we can bring up comma after we are. Uh, so yes, we can use comma, but dx and dz. First, let's try to figure out what it is in those terms. This, indeed, yes. So this is delta xi with respect to delta zj, right? And this guy is delta zj with respect to delta s, right? And that would express any one of these terms up here. And the result is going in the direction ei. Okay, so what we'll write this as is partial xi partial zj ei dyad, and I'm going to write gj. So you might wonder what is g. I haven't even introduced any g vector just yet. The idea is this, that if you have an undeformed configuration, you're going to the deformed configuration. They are both vector fields. In one case, you are describing that with respect to z, using the z vectors. Those z vectors are ones that I'm describing with the g basis vectors. Now, typically, we would not want to introduce two different bases, one for a deformed configuration, one for an undeformed configuration. We usually use the same basis vectors. So that's why I've drawn E1, G1, E2, G2, E3, G3 in the same directions. But that is not necessary. It is quite convenient sometimes actually to use two different sets of basis vectors for a deformed configuration and an undeformed configuration. So even E2, E3 and G1, G2, G3 could be pointing in different directions in general. They are just basis vectors, right? I can choose any coordinate system I want to describe some vector. The underlying vector, displacement of u, for example, is a physical quantity that I can use any coordinate system to describe. But most of the times we will be using the same coordinate system E1, E2, E3 along G1, G2, G3. But just to keep it more general, I'm going to use this description acting on DZDS, so DZKDSGK. What I have here is the tensor F, which is components partial xi partial zj. These were the 9 components in the matrix on the previous page that I was showing you. This is nothing but the components of the undeformed tangent vectors. And you can see if I try to simplify this, it comes out to basically gj dot gk. What would that be? Sorry, gj dot with gk, delta jk, and I can contract out so these go away. I can contract out k, this k replaced with j, and what we get then is partial xi partial zj times dzj ds in the direction ei. Okay, this term right here is what that big matrix shows you on the previous page. So maybe I'll put a box around this guy as well. Oops. This is a matrix of 9 terms. This is a vector of 3 terms, and in the result is being given in the direction ei, that I matches with the xi component here, which is exactly what we have up here. Partial xi partial zj dzj ds, and the result goes in the ei direction. Okay, all right, so let's maybe stop here, and there's some examples that I'll try to cover next time, but I think this will allow you to solve most of the problems on homework 4 that I've assigned, especially the calculating the lengths and calculating this tensor f for the problems. There is another tensor C and E that I need to talk about, which you can read the book or just the definition. So we'll do that next time. Okay. And once again, if you haven't submitted your paper copy for homework 2, please bring that in next time or just drop it by my office hours after you submit it online.